The causes of hyperlipidemia, a complete analysis from genetic code to lifestyle choices. Dear friends, welcome to today's health education course. I am your medical instructor, and today we will delve deep into an important disease that affects the health of hundreds of millions of people worldwide, the causes of hyperlipidemia. Opening: the shocking truth behind the numbers. Let me first share with you a set of alarming statistics. According to the latest global epidemiological surveys, more than 2 billion people worldwide suffer from various degrees of dyslipidemia, with over 400 million requiring active medical intervention. Even more concerning is that nearly half of these patients are unaware that they have the disease. Why does this happen? Because hyperlipidemia is typically a silent killer that presents almost no symptoms in its early stages, yet quietly damages our vascular system. Today we will unveil the mysterious veil of this silent killer and gain a scientific understanding of its causes. Chapter 1: Basic Knowledge of Blood Lipids, Understanding the Enemy to Defeat It. Before discussing the causes of hyperlipidemia, we need to first understand what blood lipids are. Blood lipids, simply put, are the lipid components in blood, mainly including 4 categories. 1. Total cholesterol. Normal values should be below 200 mg 5.17 millimoles per liter. Cholesterol is an important component of cell membranes and serves as raw material for synthesizing bile acids and steroid hormones. However, when excessive, it deposits on vessel walls, forming atherosclerotic plaques. Low-density lipoprotein cholesterol, LDL, known as bad cholesterol. Normal values should be below 100 mg 2.59 millimoles per liter. The main function of LDL is to transport cholesterol from the liver to peripheral tissues. When LDL becomes oxidized, it is engulfed by macrophages, arming foam cells, which is the initial step of atherosclerosis. High-density lipoprotein cholesterol, HDL-C, known as good cholesterol, levels should be above 40 mg 1.04 millimole for men and above 50 mg for women. HDL has a reverse cholesterol transport function, carrying cholesterol from peripheral tissues back to the liver for metabolism, providing anti-atherosclerotic protection. 4. Triglycerides, TG. Normal values should be below 150 mg lat, 1.70 milliliter per liter. Triglycerides are the body's main energy storage form, but when elevated, they increase the risk of pancreatitis and indirectly affect other blood lipid components. Chapter 2: Classification of hyperlipidemia. Different strategies of 2 major camps. Hyperlipidemia can be classified into 2 major categories based on its causes: primary hyperlipidemia and secondary hyperlipidemia. This classification not only helps us understand the nature of the disease, but more importantly, guides us in developing appropriate treatment strategies. Primary hyperlipidemia, the rebellion of genes. Primary hyperlipidemia, also known as hereditary hyperlipidemia, is blood lipid metabolic abnormality directly caused by genetic defects. This is like our body's traffic control system experiencing program errors, unable to normally regulate the production, transport, and clearance of blood lipids. Secondary hyperlipidemia, the invasion of environmental factors. Secondary hyperlipidemia is blood lipid abnormality caused by other diseases or external factors. This is like a normally functioning traffic system being disrupted by external interference causing traffic congestion. Chapter 3: In-depth analysis of primary hyperlipidemia. Familial combined hyperlipidemia, FCH. Let's start with the most common hereditary hyperlipidemia. Familial combined hyperlipidemia is the most common hereditary blood lipid abnormality in humans, affecting 1 to 3% of the global adult population. Inheritance pattern and prevalence. FCH follows an autosomal dominant inheritance pattern, meaning if one parent has this disease, children have a 50% chance of inheriting the pathogenic gene. According to the latest epidemiological data, general population prevalence, 0.52%. Prevalence among coronary heart disease patients, 10%. Prevalence among acute myocardial infarction survivors under 60, as high as 11.3%. Disease characteristic: the ever-changing master of disguise. FCH has a very special characteristic. Its blood lipid phenotype changes over time. The same patient may present at different times with 1. Pure hypercholesterolemia, 2. Pure hypertriglyceridemia, 3. Mixed hyperlipidemia. This variability makes FCH diagnosis complex, which is why we call it the master of disguise. Molecular mechanisms, the complex symphony of polygenic effects. The pathogenesis of FCH involves the synergistic action of multiple genes, mainly including APOA1C3A4 gene cluster, LPL gene, lipoprotein lipase gene, APOE gene, LDLR gene, low-density lipoprotein receptor gene. The polymorphisms of these genes collectively affect the synthesis, transport, and catabolism of lipoproteins. Familial hypertriglyceridemia, FHTG, genetic defects and metabolic abnormalities. FHTG is mainly caused by defects in the lipoprotein lipase, LPL gene, or its cofactor APOSU gene. Lipoprotein lipase is a key enzyme for breaking down triglycerides. When this enzyme activity is insufficient, triglyceride-rich lipoproteins such as VLDL and chylomicrons accumulate in the blood. Clinical manifestations and complications. FHTG patients typically have triglyceride levels exceeding 500 mg per L, and in severe cases can reach 2,000 to 5,000 mg per L. Such extremely elevated triglycerides bring serious complications. 1. Acute pancreatitis. When triglycerides exceed 1,000 mg per L, the risk of acute pancreatitis increases dramatically. 2. Increased blood viscosity may lead to retinal vascular disease. 3. Cardiovascular disease risk. Long-term high triglycerides increase the risk of cardiovascular events. Familial hypercholesterolemia, FH. Although not detailed in the content you provided, FH is another important type of primary hyperlipidemia. Gene mutations and receptor dysfunction. FH is mainly caused by mutations in the LDLR gene encoding LDL receptor, APOB gene, or PCSK9 gene. These mutations result in reduced numbers or dysfunction of LDL receptors on hepatocyte surfaces, preventing effective clearance of LDL cholesterol from the blood. Clinical features. Heterozygous FH patients typically have LDL cholesterol levels of 200 to 400 mg/dL. Homozygous FH patients can have levels of 600 to 1,000 mg/dL or higher. Typical skin xanthomas, tendon xanthomas, eyelid xanthelasma. Early onset coronary heart disease, men 55 years, women 65 years. Chapter 4. Secondary hyperlipidemia, the price of modern life. Disease-related secondary hyperlipidemia. Diabetes and insulin resistance. Diabetes is one of the most common diseases causing secondary hyperlipidemia. Up to 80% of diabetic patients have concurrent dyslipidemia, mainly manifesting as elevated triglycerides, usually 200 mg/dL, decreased HDL cholesterol, increased small, dense LDL particles. Mechanism analysis. Insulin resistance leads to increased hepatic VLDL synthesis while affecting lipoprotein lipase activity, causing reduced triglyceride clearance. Hypothyroidism. Thyroid hormone is an important hormone regulating lipid metabolism. During hypothyroidism, up to 90% of patients develop hypercholesterolemia, mainly due to reduced LDL receptor expression, increased cholesterol synthesis, decreased bile acid synthesis. Kidney disease. Chronic kidney disease and nephrotic syndrome almost 100% involve blood lipid disorders. Nephrotic syndrome mainly presents as high cholesterol and high triglycerides. Chronic renal insufficiency, primarily triglyceride elevation and HDL reduction. Liver disease. The liver is the center of lipid metabolism, and liver disease causes complex blood lipid changes, chronic hepatitis, triglyceride elevation, cholestasis, significant cholesterol elevation, fatty liver, usually accompanied by metabolic syndrome. Drug-related hyperlipidemia. Certain medications interfere with normal lipid metabolism. Corticosteroids. Long-term use leads to elevated triglycerides, decreased HDL cholesterol, fat redistribution. Beta blockers. Particularly non-selective beta blockers cause 10 to 20% triglyceride elevation, 5 to 10% HDL cholesterol reduction. Diuretics. Thiazide diuretics cause elevated triglycerides, slight total cholesterol elevation. Chapter 5. Lifestyle factors. The double-edged sword of modern civilization. In-depth impact of dietary factors. Saturated fatty acids, the manufacturing plant of cholesterol. Saturated fatty acids mainly come from animal foods such as red meat, dairy products, and coconut oil. They upregulate HMG-CoA reductase activity, promoting cholesterol synthesis, downregulate LDL receptor expression, reducing cholesterol clearance. For every 1% increase in saturated fat intake, LDL cholesterol rises approximately 2 to 3 mg. Trans fatty acids, the corrosive agent of blood vessels. Trans fatty acids have the most adverse effects on blood lipids among all fatty acids. Elevate LDL cholesterol, lower HDL cholesterol, increase inflammatory response. For every 1% increase in trans fat intake, coronary heart disease risk increases by 23%. Simple sugars, the catalyst of triglycerides. Excess simple sugars activate fatty acid synthase that promote hepatic lipogenesis, increase VLDL secretion. High fructose diets particularly easily lead to triglyceride elevation. Metabolic consequences of lack of exercise. Key role of lipoprotein lipase activity. Exercise can increase lipoprotein lipase activity 2-3-fold, increase HDL cholesterol 5 to 10%, reduce triglycerides 10 to 20%. Scientific basis for recommended exercise volume. According to American Heart Association recommendations, moderate intensity aerobic exercise, 150 minutes per week. High intensity aerobic exercise, 75 minutes per week. Strength training, twice per week. Each exercise session should last at least 10 minutes. Complex effects of obesity. Special harm of visceral fat. Visceral fat, abdominal obesity, has a greater impact on blood lipids than subcutaneous fat. Releases more free fatty acids, increases hepatic lipid synthesis, promotes inflammatory response. For every 1 centimeter increase in waist circumference, triglycerides rise approximately 2 to 3 milligrams per yalers. Endocrine function of adipose tissue. Modern medicine recognizes adipose tissue as an active endocrine organ that secretes leptin, regulates appetite and metabolism. Adiponectin improves insulin sensitivity. Inflammatory factors such as TNF-α, IL-6. Multiple harms of smoking. Smoking's effects on blood lipids are multifaceted. Decreases HDL cholesterol 10 to 15%, increases the proportion of small, dense LDL, promotes LDL oxidation, damages vascular endothelium, increases thrombotic risk. Dual effects of alcohol. Moderate versus excessive alcohol consumption have vastly different effects on blood lipids. Moderate alcohol consumption, men 2 units a day, women 1 unit a day, increases HDL cholesterol 5 to 10%, improves insulin sensitivity, has anti-inflammatory effects. Excessive alcohol consumption significantly elevates triglycerides, excessive hepatic VLDL production, increases liver disease risk. Chapter 6. Gene-environment interactions, the perfect storm of disease occurrence. Quantitative analysis of genetic susceptibility. Modern genetic research shows the degree to which blood lipid levels are influenced by genetic factors. Total cholesterol, 40 to 60%, LDL cholesterol, 50 to 60%, HDL cholesterol, 40 to 50%, triglycerides, 40 to 60%. This means that while genes are important, 40 to 60% of variation is still determined by environmental factors, providing us with opportunities for intervention. New discoveries in epigenetics. How lifestyle rewrites genes. Recent research has found that lifestyle can affect gene expression through epigenetic mechanisms: DNA methylation, histone modification, microRNA regulation. These mechanisms can turn on or turn off specific genes, affecting cholesterol metabolism, and may even be passed to the next generation. Examples of gene-environment interactions. APA gene polymorphism. The APA gene has 3 main alleles, E2, E3, E4, and their interactions with environmental factors. APOE4 carriers are more sensitive to saturated fats. ApoE2 carriers are prone to triglyceride elevation. Dietary interventions have different effects on different genotypes. 9p21 chromosomal region. Variations in this region are associated with early-onset coronary heart disease, but environmental factors significantly influence its expression. Smoking amplifies genetic risk 2 to 3-fold. Healthy diet can partially offset genetic risk. Regular exercise has protective effects. Chapter 7. Effects of age and gender. Blood lipid changes throughout life cycle. Childhood. Relatively low blood lipid levels. Hereditary hyperlipidemia may already be manifest. Period of establishing lifestyle habits. Adolescence. Effects of sex hormones begin to appear. Male HDL begins to decline. Females relatively protected by estrogen. Adulthood. Blood lipids gradually rise. Effects of life stress and work patterns. Peak period for metabolic syndrome. Menopause. Female estrogen decline. Rapid blood lipid deterioration. LDL cholesterol can rise 30 to 40%. HDL cholesterol decreases 10 to 15%. Mechanisms of gender differences. Male characteristics. Naturally lower HDL cholesterol, tendency toward visceral fat distribution, earlier onset of atherosclerosis. Female characteristics, protective effects of estrogen, primarily subcutaneous fat distribution, rapidly catch up to male risk after menopause. Chapter 8. Relationship between inflammation and blood lipids. Role of chronic inflammation. Modern medicine increasingly recognizes the important role of chronic inflammation in hyperlipidemia. How inflammation affects blood lipids, promotes hepatic acute phase protein synthesis, alters lipoprotein composition, accelerates LDL oxidation, affects HDL's anti-inflammatory function. Clinical significance of inflammatory markers. C-reactive protein CRP reflects systemic inflammatory status. Interleukin-6 IL-6 pro-inflammatory cytokine. Tumor necrosis factor TNF-A affects insulin sensitivity. Therapeutic targets for inflammation. Controlling inflammation has become a new strategy for blood lipid management. Anti-inflammatory effects of statins, anti-inflammatory action of omega-3 fatty acids, comprehensive effects of lifestyle intervention. Chapter 9. Emerging risk factors. Lipoprotein A, L, unique structure and function. Lipoprotein A is a special lipoprotein composed of LDL-like particles and a polypop. Protein A, 90% determined by genes, normal values 30 mg per deciliter, has prothrombotic and pro-inflammatory properties. Clinical significance, independent cardiovascular risk factor, limited effectiveness of traditional treatments, important target for new drug development. Small dense LDL, S pathophysiological characteristics, smaller particles, diameter 25.5 nanometers, more easily oxidized, more easily penetrates arterial walls, associated with elevated triglyceride detection and treatment, electrophoretic analysis or NMR detection. Controlling triglycerides is key. Niacin and fibric acid derivatives are effective. Apolipoprotein B, ApoB, more precise indicator than LDL, represents the number of all atherogenic lipoproteins, unaffected by lipoprotein size. Men 90 mg dili, women 80 brilite. Chapter 10. Blood lipid management in the era of precision medicine. Personalized risk assessment, polygenic risk score, integrates cumulative effects of multiple genetic variants, identifies individuals with high genetic risk, guides early intervention, predicts treatment response. Applications of artificial intelligence, big data analysis, machine learning prediction models, personalized treatment recommendations, precision treatment strategies, gene-directed treatment selection. LDLR mutation carriers prioritize statins, PCSK9 variant carriers suitable for PCSK9 inhibitors. APOE genotype guides dietary treatment. Biomarker-guided treatment, inflammatory markers. Consider anti-inflammatory treatment. Lipoprotein A special treatment strategies. Insulin resistance, metabolic modulators. Our conclusion, health strategies for the future. Dear friends, through today's detailed explanation, we have gained an in-depth understanding of the complexity of hyperlipidemia causes, from genetic rebellion to environmental invasion, from single factors to multiple interactions. The occurrence of hyperlipidemia is a complex process. Key message summary. 1. Genetics is not destiny. While genes are important, lifestyle can still significantly affect blood lipid levels. 2. Prevention is better than treatment. Understand your family history and establish healthy lifestyle habits early. 3. Individualized strategies. Each person's genetic background and environmental exposure are different, requiring tailored prevention and treatment plans. 4. Lifelong management. Blood lipid management is a lifelong process requiring continuous attention and adjustment. Specific recommendations for everyone. 1. Regular checkups. Starting at age 20, check every 5 years. Those with family history should monitor more closely. 2. Healthy diet. Reduce saturated and trans fats. Increase fruits, vegetables, and whole grains. 3. Regular exercise. At least 150 minutes of moderate intensity exercise per week. 4. Quit smoking and limit alcohol. Complete smoking cessation, moderate alcohol consumption. 5. Weight control. Maintain healthy weight and waist circumference. 6. Stress management. Learn appropriate stress relief methods. Remember, we are not powerless in the face of hyperlipidemia. Science has provided us with abundant knowledge and effective tools. The key is whether we are willing to act. Let us start today. Take responsibility for our own and our family's health, and together welcome a healthier future. Thank you for listening. I hope today's content has been helpful to you. If you have any questions, please feel free to discuss them with healthcare professionals at any time. Health is our most precious wealth. Let us protect it together.